Welcome students. We are back with another lesson. In this lesson, we'll discuss diffraction of light. What is diffraction of light? Now, before we understand diffraction of light, let me give you a situation. Suppose you have a music player which is placed on the other side of the wall. Fine. And suppose you are staying on the other side of the wall. So the question here arises, if the music starts playing from this music player, will you be able to hear its music? Yes. Why is it so? Like, see, your music is on the other side of the wall. Still, you can listen to or you can hear the music. Why is it so? This is because the sound waves, okay, the acoustic waves, generally what happens? They bend across the wall. Suppose the music is coming somewhere from here, okay? This music coming from here, it bends to give sound in all direction, right? So can you see the phenomenon of the bending of waves to reach to the destination? Okay, the sound waves bends and reaches the receiver or observer. A similar phenomenon is observed in lights. So suppose if you have a light source, fine, this light source is placed behind a single slit. This is your single slit. Now, if this, the condition here is that the size of this slit, okay, the size of the slit should be comparable, okay, it should be equivalent to the size of the wavelength, okay, this is your wavelength, fine. So the size of this slit, the size of the slit should be somewhat same about the wavelength, fine, or it can be smaller than the wavelength, not greater than the wavelength, fine. So if this slit size is smaller or equivalent to the size of the wavelength, okay, wavelength of what? Of the light coming from this light source, what will happen is that the light will bend, okay. So you can understand like this also. Suppose if I place a screen out here, okay, suppose if I placed a screen out here. Now, what do we expect? We expect that the light will come and whatever the amount of the light which can flow through the slit will fall on the screen like this. Fine. This is what we expect. Now, if the size of the slit is smaller or comparable to the wavelength of the light coming from this source, then in that case what happens? The light waves, just like your sound, okay, just like your sound waves, what happens? This light waves will bend around the corners by a small amount, fine. The light bends around the corner in the small amount, therefore you will get a bigger spot on the screen, fine. Actually, what we expected only this much spot on the screen, fine. But we are getting much bigger spot on the screen. And why is it so? This is because of the phenomenon of diffraction, where the light bend around the corner of your aperture, fine. This slit, okay, we also call it as aperture. So let's take an example, fine. In this case you can see that the light, this light is coming in form of a plane wave, okay. Your red one represents the crest, the blue one represents the trough. So as they approach towards the slit, okay, this small part, this represents your slit. Now when they propagate or when they pass through the slit, okay, here in this case, the slit size is equivalent to the size of the wavelength. Fine. Now what happens to this light? Can you see? The light, instead of traveling in a straight path, it is getting bent around the corners. Fine. Can you see? This part was supposed to be dark like this part, okay? But it's not dark like here. Why? Because the light is getting bent around the corners of the aperture. This phenomenon of bending of light is known as your diffraction. Fine. Okay. Let's take one more case. Suppose you have a light. Okay, the light is coming from this source. Fine. Now let us suppose if I place a obstacle in the path of the light. Fine. What does it means? Like suppose consider you have a light source, okay? And I have placed a screen here. So if there was no obstacle, what happens? The light will illuminate the screen, okay? It will fall at all points on the screen. So the screen will be illuminated by this yellow light. Fine. Okay, this is the scenario. Now what we will do? Now let us put a obstacle here. Fine. Let me put a obstacle here. Now as soon as you put the obstacle, what do you expect? We expect that all of the portion will be bright except the one which is behind this obstacle. Fine. Rest all of the region of the screen will be illuminated by the light. Only a small portion, okay, only small portion will not be illuminated by the light. Rest all of the screen will be illuminated by this light. Now why is it so? This is because of the obstacle which we have placed in the path of the light. Fine. But as you look carefully, okay, what happens in this case is that the size of the shadow, okay, the size of the shadow is not as equivalent to the size of the obstacles. Now why is it so? This is because in this case what happens, the light wave which comes, it bends around the corner and it illuminates the little part of this shadow as well. Fine. Similarly from here, the light comes due to diffraction, it comes and it bends around the corner. Therefore, we get a region which is brighter. Fine. The region which is brighter. Fine. And why is it so? This is because of the phenomenon of the bending of light, which is known as your diffraction. Fine. So you can take an example. In this picture you can see your tree is acting as a obstacle. Fine. And your source is your sun. Fine. So the light rays coming from the sun are getting bent. Fine. They are bending. That's why, can you see at this region, what you notice is that the shadow is not proper. Okay, why is the shadow not appearing properly? Because the light is being bent around the corners of the obstacles. Fine. So now we can answer, what is diffraction of light? The phenomenon of bending of light around the corners of small obstacles or aperture and its consequent spreading into the region of geometrical shadows. So we have discussed the two cases where we have allowed the light to pass through a narrow aperture. Now when the light passes through the narrow aperture, what happens? This region, okay, this region should be the region of the geometrical shadow. But what happens? Due to the diffraction, the light bends around the corner. Therefore, the size of this bright spot increases, whereas the size of this geometrical shadow decreases. It reduces. Fine. The similar phenomenon is observed here also. In this case, what happens? The source is placed very close to the obstacles. Okay, fine. In this case, the light bend outwards. Fine, the light bend outwards. This phenomenon of bending of light outwards is known as the diffraction of light. Okay, in my previous example, I've explained that I've showed that the light bend inwards, but here in this diagram, it has been shown that the light bend outwards. Okay, so this type of diffraction, okay, this type of diffraction can be categorized further into the two categories, your Fresnel diffraction and your Fraunhofer diffraction. Okay, this Fresnel and Fraunhofer diffraction is not for your syllabus right now. Okay, for now you can just understand the phenomenon in which the light bend around the corner. Okay, the bending can be outwards, the bending can be inwards. This bending depends upon the distance between the source and the screen. Okay, we will not get into this one, right? This is something which you will study in your higher classes. Your Fresnel diffraction, your Fraunhofer diffraction. Fine. For now, you can only concentrate on this point, the point where the light bend around the corners of the small obstacle to create a region of a geometrical shadow. This phenomenon of bending of light is known as your diffraction. Fine. Okay, so in our next class, we'll discuss diffraction at a single slit. Okay, now in this topic, we will describe the phenomenon of diffraction of light through a single slit. Okay, so what we will do is we will introduce a small aperture. We will introduce a small aperture. Fine. This is your single slit. Fine. Now what we will do, we will place a source S here. This source will produce the light waves. Fine. Now what will happen, as we have studied, the light waves will bend around this aperture to obtain the image on your screen. Okay, it will. Now if you look properly into this region, okay, let me just zoom in. Fine. Now what you will notice is that the light which travels from this point, okay, let us say this point A, this point B. Fine. Let us give the slit a name, point A and point B. Fine. Now the light which travels from this point A and the light will travel from this point B. Now what we will do, we will introduce a concave lens. Sorry, we will introduce a convex lens. Fine. Now, when the light passes through the convex lens, what will happen? It will focus at a particular point on the screen. Okay, let me name this point as point O. Fine. Similarly, the light which is coming from your point B will also pass through the lens and it will get converged to this point O. Fine. So you have the light waves coming from the two corners of the aperture. Now, if you notice that the light which comes from the two corners, from here and from here, they are traveling the equal path. The distance traveled by this light AO and the distance traveled by the light BO is equal. So in such case, there is no path difference. If there is no path difference, what happens at this point? Or what you will notice? You will notice a bright fringe. Fine. Now look here again. Okay. Now consider there are see this point A acts as a source of your secondary wavefront. That means the light will be traveling in all direction from this point. Okay. Now suppose there's a light which is moving at a slightly different angle. The light which is moving slightly at a different angle. It comes and it falls on the screen at this point. Fine, it get converges at this point. Similarly, the light is coming from point B and it falls on this point. Okay, and let me name this point as P. Now, in this case, okay, what you notice is that whether the light which is traveling from point A to point P, is it traveling the same distance as the light which is traveling from B to P? No. In the point B, the light is traveling some extra distance. Fine. If you look, see, if I'll say this, the bend in the amount of the light is theta. Fine. If the light bends by an angle theta, so consider an angle theta here also. Fine. So in this case, what you will notice is that the light which is traveling from B, okay, this green part, this green line, this is the extra path which is traveled by the light which is coming from point B. Fine. Just imagine if the light, if the point B was here, if the point B was here, okay, to remove this bending of light, okay, to remove this bending of light, what I have done, I've moved this B by a certain angle theta. Fine. So consider this case. In this case, what happens? The light which travels from point A and the light which travels from point B, they travel same path. Fine. But it is the actual case? No. In actual, the light has to travel this extra path in this case. Okay. Now, if the light has to travel an extra path, that means a path difference will come into the picture. If the path difference comes into the picture, then what will happen? Then we will observe the interference pattern depending upon the path difference. So depending on the path difference, we will get a maxima pattern. Depending on the path difference, whether we'll get a minima pattern. Okay, we will see this in our next class. Fine. Okay, before I leave this topic, okay, let me just show you the experiment. Okay, so if you take a look in this case, okay, this person has made a single slit out of this can box. Okay, now if he opens, now if you see, he opens his can box cap. Now what he has done is that he has created a single slit. Can you see? This is a single slit. How he has created a single slit? He has created the single slit by placing two blades. Okay, by placing two blades very close to each other. So by placing the blades very close to each other, he has created a small gap at this point. This will act as a single slit. Okay, and why do we need this small gap? Because this small gap is comparable. Okay, it is equivalent to the size of the wavelength of the light which he'll use. In this experiment, he will use, so in this experiment, he'll use this laser. The wavelength of this laser is equivalent to the size of this slit. Okay, so what he will do, he will make the laser light pass through this single slit. Okay, can you see the light which is coming from behind? This light, okay, it represents the laser. Fine, this light passing through the slit is your laser. Now what he'll do, he will obtain this image on the screen. Fine, now when he obtained the image of the screen, can you see at the center the maximum of the light falls, so he will get a maximum. But at this point, okay, where there is a part difference coming into the picture, and part difference also such that which results into destructive interference, so at those points you will get a dark fringe. Can you see this black spot here also? This is your dark fringe. Similarly, the regions where the two waves of different part difference interfere constructively, at those places you will get a light of maximum intensity. So this is maxima. So similarly, in your diffraction through a single slit, you will obtain an image, or you can see this phenomenon of this, where you'll see the interference pattern being obtained on the screen. And why is this interference pattern being obtained? This is because of the diffraction of light, the bending of light. Fine. So this bending of light, or your diffraction of light, I'll discuss it in my next class. Fine. And the link for those videos, okay, I'll give it to you in this PDF. Fine. So So that's it for today's class. Thank you. And if you have any confusion, please don't hesitate to ask. I will re-explain it to you again. So again, thank you.